I'm your host, Grayson Brulte. Welcome to another episode of SAE Tomorrow Today, a show about emerging technology and trends in mobility with leaders and innovators to make it all happen. On today's episode, we're absolutely honored to be joined by Philip Riegler, Product Manager at Norsk Titanium. On today's episode, we'll explore how additive manufacturing is changing aerospace. We hope you enjoy this episode. Philip, welcome to the podcast. I got to say, additive manufacturing plays a very important role in society, and I'm really glad that you're here to shed some light on it today.
Well, first, I want to say thank you to SAE for having me on the podcast today. It's a privilege of mine to be here. I'm excited to get into this conversation a little bit and demonstrate a little bit more about what additive manufacturing enables and get into the nuts and bolts of it a little bit if we can.
Oh, absolutely. Additive manufacturing plays a large role in aerospace. Why did Norsk Titanium decide to focus on structural aerospace parts?
That's a really good question. When you look at the airframe of an aircraft, a lot of the large parts are forgings, and they're titanium forgings. And because there's a high use of titanium in the airframe structures, the application of our technology lends itself to a one-to-one replacement of them. From a perspective of titanium utilization in the world, titanium for aerospace ranks at the very highest of quantity of titanium used in the world.
Wow. Has titanium always historically been a key component of aerospace?
Originally, it was aluminum, but as we start getting into the composite structures and things of that nature and need to have some stronger material behavior with less weight, it has transitioned to titanium, yes.
And if you look at your company's history, the company first started having parts fly in the Boeing 787. How has the approach to quality changed since that first moment?
Our quality system hasn't changed from day one. Our quality system has always been aligned with AS9100, which is the quality system for aerospace parts manufacturers. We specifically formatted our quality systems to focus on aerospace from the very beginning. And we have been in conformity to the aerospace manufacturing and quality standards since. So it was a insight and a direction that we took with the intent to be an aerospace manufacturer.
So it basically goes down to, if you want to say, the foundation of the company to get the AS910 certification from the beginning?
That's correct, yes.
And so, because if you look at it, so the company recently entered into a serial production deal with Airbus for certain parts of the Airbus A350. What does a ramp-up period look like? Because Airbus A350, they're a very common plane. It's like, oh boy, there's a lot that goes into this. What does a ramp-up look like?
So the ramp-up period post-qualification, it's taken us about 2 to 3 months to fully saturate the value stream. And what I mean by fully saturate is that's just the parts keep coming out at a standard average pace where we can expect a certain volume of parts per month. And we just feed the value stream much like any other product, but it has taken 2 to 3 months to reach the steady state where we are now with that application.
For the audience that might not be familiar with the value stream, how would you define the value stream for the audience?
Oh, sure. The value stream for aerospace parts, specifically for Norsk Titanium, we are a material manufacturer. We print raw materials from which aerospace parts are harvested. Following the actual additive manufacturing in our manufacturing cell, the material is sent to a stress relief operation and then followed by either simple machining to enable non-destructive testing, 100% volumetric non-destructive testing, or to final part shape and then non-destructive testing. Following the final part machining, the parts are shipped back to us for the final certificate of conformity. So the value stream is really the downstream processes that lead to the ability to manufacture those parts.
And the company uses a wire-fed process with titanium. What does that look like, and what does it unlock for your customers?
The wire type AM system is one of the older types of manufacturing processes. It's typically referred to and can be aligned with wire welding, where you have an energy source, you have a wire going through the energy source, you're laying a molten pool on some substrate or on consecutive build layers. We print about a 10 millimeter wide deposition string. So each string is about 10 millimeters wide, and that gives us the ability to deposit a lot of material very rapidly. When we look at what that does for our customers, is it gives us the ability to rapidly produce material, but at the same time, we're able to put material only where the material needs to be. So you're not machining away additional material from a casting or a forging or from a plate product. So you're reducing waste. It gives an alternate part path over castings and forgings, and we are able to iterate a little bit more rapidly than some of the legacy processes.
How much waste do you eliminate then as it's compared to traditional forging?
We are able to save between 10 and 50% waste over the traditional manufacturing processes.
10 to 50%. That's a big number. How do you do that?
Yeah, that's a big number. It really comes down to if you've got cavities or large empty spaces, you're going to buy a piece of billet that is going to be rectangular in nature, for instance, and you're going to machine all of those cavities away. Instead of machining those cavities away, we just don't put material there. And that material that we don't put there is not introduced into the waste stream. We like to refer to it as a buy to fly ratio, where it's the amount of titanium that you need to have versus the amount of material that ends up in the final part.
Seems that it's a simple process, but I'm going to sit here and say it's not. It's probably a very complex process, but you're doing a lot of good with a 10 to 50% savings. It's good for the environment. It's good for your business. It's good for your customers. In simple terms, how was the process invented, or was there a aha moment internally said, wait a second, we could eliminate all this waste?
The process was invented. The intent was to improve the downstream titanium supply chain. Raw product, the making of the ore, making of the sponge is a very process intensive, very highly energy inefficient process. Taking it from a plate or a drawn wire gives you the opportunity to change the way that you introduce material into the downstream process. It was landed on the wire and plasma due to the fact that wire is easily available and it requires less handling than powder technologies. We did evaluate powder technologies early on. And then the plasma arc welding system that we use has a very broad and strong energy density. So we're able to, back to a previous comment, where we're able to deposit very wide strings very rapidly. And so it was determined that the combination of those gives us the best opportunity to be able to produce large materials at very rapid rates.
So you're doing good for the environment by saving waste, which is also very, very, very good for the company. You're unlocking speed, which again is great for the company and great for your customers. Now, the other part of the equation is weight. And some manufacturing purposes for additive manufacturing, not yours, you have weight limitations and you can't go very heavy. How weight? Can you go heavier than your traditional additive manufacturing? What does that look like?
We have one product in the industrials market that weighs over 80 kilograms in the as deposited condition. And I can't go into specifics about how much higher than that we can go, but it's really the limitation of the axis itself that supports the carrier and the RPD material. So we'll just leave it there.
We can leave it there, but I'll just say in simple terms, that's impressive. The fact that you can achieve that weight is very, very impressive.
Yeah, compared to other manufacturing processes, we have the system set up to be able to handle those weights, those masses, and in some instances higher than that. And that really does enable and unlock a large portfolio of parts that the smaller additive processes cannot do.
And I'm going to take this back to a lot of listeners aren't really familiar with additive manufacturing. For a casual listener, how would you explain the company's approach to additive manufacturing? Because you got the speed, you got the reduced waste, and you got the weight. So you've got all the, as you call the ingredients or the elements to a casual listener. How would you explain that approach?
We like to think of it as layers of an onion. We start with the final part geometry as the center of the onion, and then we build materials surrounding that to get to the necessary material requirements to be able to enable 100% volumetric inspection on every part, to have machining tolerances, to have for final part machining, as well as meet the minimum tolerances for dimensional conformity, give some real estate so that the machining vendors can find the part. And so once we meet those really three independent metrics, that's how we define the boundaries of our print envelope.
That's really good. So obviously we're talking about aerospace here. So in order for additive manufactured parts to be certified for aerospace, what has to be done? Is that the AS910 certification, or is there another certification? I know you mentioned your partners, but as we know here in the United States, aerospace is highly regulated. So I'm curious if there's anything else that has to go into that process.
No, the process itself, once you have a fixed frozen process, whether it's a forging or a casting or other manufacturing process, once that process is qualified, you're able to go directly into production where those type certificate holders, those design authorities say that, yes, the parts can be implemented into that. We've done our engineering justification there too. So it's more of the effort to get through the qualification by answering the customer's request for additional material, for additional testing, different testing campaigns. It's been a long time that we've been in different testing campaigns with different customers, and we see new testing campaigns just about every 6 months or so because we get a new customer that's interested in evaluating the material. And once there's an engineering understanding of the material, it's much easier for them to do the justification for implementation across whichever platform they happen to be evaluating the material for.
When you say testing, I put on my I'm a big kid hat and I think of the right stuff. Okay, we got test pilots and test planes, and so that's the kid in me. Is that when you say the test the part? Is that going on a test plane? Is that going into a factory or some simulation environment to test it, or is the kid in me getting ahead of myself?
Yeah, getting a little bit ahead of yourself. The testing campaign is much less fancy than that. We create componentry, we send it to a mechanical testing house, and they will cut coupons for ASTM E8 or other standard ASTM mechanical testing processes, and they'll put it in their test fixture and they will break the part, and then they'll do an analysis of the resultant, whether it be a fatigue result or a tensile result, and then they will consolidate all of that and put that into their package. So the testing is really just a lot of testing at a mechanical test facility, characterizing how the material behaves in certain applications.
Once the part's certified, it's on a plane, let's say it's being used in commercial applications, how do you track its performance and health over, say, a 20 or 30-year period of flight?
Well, that's a really great question. We don't have any visibility to that. That's up to our customers to define, and we've not been privy to that. But as one would surmise, that's absolutely something that is going to be tracked and traced. So, but at this point, what those plans are for our customers, we don't have any real line of sight to how they're evaluating it or plan to evaluate it.
It seems to me, based on this conversation, that your customers play a very large role in the relationship.
They're the primary drivers.
Staying on that, so obviously some of your customers are aircraft manufacturers. This is just a general question. What does additive manufacturing solutions unlock for them that wasn't possible before?
Sure. What it unlocks for them is a design for a new paradigm. When you start to look at the legacy processes, they're very blocky, very square type shapes. We know that square type shapes don't do well with aerodynamics. When we look at designs of the future, we're looking at some very neat, curved, integrated structures. Legacy products to do that have a lot of bolted connections. They have a lot of fasteners. Anytime you had a fastener or any sort of hole in a material where there's a load applied across it, it has the opportunity for there to be cracking in their life cycle. When you start to take that out, you can start to reduce the thickness of the material in those areas and still have the same engineering safety factor. So you can take a reduction of, say, 3 parts that are bolted together. You can make them as one assembly, and you can then reduce the amount of total mass because you've increased the engineering safety margin by reducing those fastener locations. That's one example. I'm sure there are others that are more important in different applications, but that is one that we have seen a request for a reduction of a 3-piece assembly to a 1-piece additive manufactured part.
Okay, so from a repairs perspective, it seems that this is just hypothetical. I'm not an expert in this. It seems that additive manufacturing could accelerate the repair of a part, or to print a part, if you want to use that term.
From the repair perspective, that's our intent, is to place our machines at an MRO where they do that type of operation. We're not sure what the future holds for that, but being located where those repairs happen or a new part production needs to occur, of course, is beneficial for the MRO for returning the aircraft to safe flight service.
And to me, it eliminates the downtime. You could potentially shorten the downtime if you had access to these tools. So there's a lot of good there.
There's a lot of good there. And as this technology matures, as additive manufacturing becomes more of a baseline, we're expecting to see things of that nature and maybe some other unique applications coming to light.
So that's on the civilian side. On the defense side, the company recently expanded a partnership with General Atomics. How does production differ from civilian to defense applications from an aircraft perspective?
To be completely forthright, the manufacturing requirements are exactly the same. And the reason I say that is because our properties are inherent to our manufacturing process. Our manufacturing process has been proven to be equivalent across all of the different criticalities. Of course, we're not in the highest criticality. It's a crawl, walk, run approach. With any technology, you start with lesser critical structures, and as you get flight hours and experience with that material, you start to understand how it's going to behave. You walk up that criticality ladder. But to date, the actual production doesn't vary. The downstream process doesn't vary. Some of the means or the requirements for acceptance criteria may change based on the criticality of the part, but holistically, from a production standpoint, we use the same key process parameters for the different geometries.
Wow, that's really insightful. Okay, so let's stay on quality control, because right now you're in Norway, but you also have operations in New York. So how do you can have the consistency if a part's printed in Norway or a part's printed in New York from a quality standpoint? Okay, it's exactly the same. How do you ensure that?
We have the systems themselves undergo a 90-day calibration window. And with any calibrated system, we have an as found, as left condition log for the systems themselves. In those 90-day windows, we see a comparative material coming off of those systems, no matter which system in our fleet we choose to use. We use the same raw products. We use the same plate. We use AMS 4911 plate. We use Tie 64 wire with the same manufacturing routes. Again, it's a fixed frozen process. So if you have the same inputs to the system, you have the same parameters for creating the product, you get the same outputs, and that's been statistically aligned and evaluated over the about 10 years we've been in serial production with Boeing and with the testing campaigns that we've done with other customers. So that inherent consistency of the product has proven itself to be part of the fixed frozen process. That's with the material coming out of the system. Now, when we start looking at the downstream, we use a fixed frozen downstream process as well. So we use the same stress relief vendors, we use the same NDT vendors, we use the same machining vendors. So really, it's once you establish the approved supply route, as long as you follow the approved supply route, you're going to get consistent material properties regardless of where the initial material comes from.
Well, let's shift to the supply chain here, because the supply chain is in the news. You can't even go over a weekend without hearing about the supply chain. What impact has the global titanium supply chain issues had on the company over the last few years?
Well, everyone knows the supply of titanium was reduced. That's no secret. as well as the availability of the sponge, which is the base foundation, whether it's plate or forgings or ingots or sponges, where it all starts. It's still developing customer by customer what the restrictions are on utilization from different countries. But what we have seen is that for a while, we were seeing some renewed interest from some customers to see what sort of relief we could provide them in the supply chain. And some of that matured, and we have some really good opportunities that have been presented to us. And some of them, because it wasn't a long term, hasn't turned out to be as long term as they initially feared. The development cycle to get into the engineering confines and assurances is longer than what is taken for the titanium market to rebound.
That's the markets. And this is just a personal opinion on what are the most ideal use cases for this groundbreaking technology that the company has developed?
Large parts, large structural titanium forging replacement, the parts that have 26 to 50 week lead times, the ability to meet the surge demand for those products and be a solution to a stretched titanium industry. That's where the rubber really meets the road. A future state being a baseline material for the future aircraft. We have the ability to be the initial designed around material for the next generation aircraft.
If you look at today, so we're in 2026, and let's say 10 years out, what do you see being printed in the future that wasn't physically possible today?
I think what you're going to see is we're going to see a lot of really large, really complex parts coming out. And I want to take a look and shine some light over at the space industry. And there's a space manufacturer that has done great work with large format additive, and they've reduced, last I saw, something like 100-part product into one, right? So being able to, again, design fuel passages and optimize material flows, reduce drag coefficients. I see it being most applied to those large structures that the industry base has kind of not supported well over the years, whether it be pressure vessels and other hard to come by materials. I think that as the additive industry expands, we're going to start to see that, well, yes, there will be some limit. There always is some limit. I think that we're going to continue to see companies expand that and really start to push what we can do with additive manufacturing.
That's wonderful. When you look at a finished part today, can you tell that it was printed 3D using additive manufacturing, or does it look exactly like a traditional forged part would look?
When you look at the finished machine part in a side-by-side comparison, they're indistinguishable from each other. When there is a telltale, however, for additive manufacturing, if you get very close to the part after a post-machining etch, you can see the history fingerprint of the additive product as compared to the forging. But if you're a foot or 2 foot away, you're never going to see the difference in the material or the part.
I like that. See, details matter, Philip, and thank you for highlighting that wonderful detail. This has been a really insightful conversation. As we look to wrap up today, what would you like our listeners to take away with them?
I would like the listeners to take away that additive has potential. There's promise. There really is opportunity for all the additive manufacturing processing in the industry space, and whether it be aerospace or automotive or space or wherever it is another tool in the toolbox. It's never going to replace all of the legacy manufacturing processes. I don't think that's where its sweet spot is. It's another tool in the toolbox to provide a solution. And as we start to continue to look at the future for critical applications and things of that nature, we will get the processes and the products into those critical applications. It's going to take some time. Every new product and process does. But the future of additive is here. We're living it, we're flying it, and we're going to continue to see the growth in this market. provided we have the engineering judgment and the analysis of the materials and the processes for the respective applications, and that we're continuing to have new additive manufacturing systems come along and be presented and be developed and be modified, and it's endless. Additive manufacturing is here, and it is a solution to material constraints and material waste and energy consumption. It increases capacity throughput. There are so many benefits to additive that I don't see it not being successful here and into the future.
Additive manufacturing is here today. Additive manufacturing is scaling and it plays a critical role in aerospace. Today is tomorrow. Tomorrow's today. The future is Norsk Titanium. Philip, thank you so much for coming on SAE Tomorrow Today.
Thank you so much. It's been a pleasure.
Thank you for listening to SAE Tomorrow Today. If you've enjoyed this episode and would like to hear more, please kindly rate, review, and let us know what topics you'd like for us to explore next.
SAE International makes no representations as to the accuracy of the information presented in this podcast. The information and opinions are for general information only. SAE International does not endorse, approve, recommend, or certify any information, product, process, service, or organization presented or mentioned in this podcast.